Welcome, dear listener, to this gentle journey into one of nature's most enchanting performances. Tonight, we'll explore the aurora borealis and aurora australis, those mysterious curtains of light that dance across our polar skies like whispered secrets from the cosmos itself. As you settle into this quiet moment, perhaps you'd like to share in the comments where you're listening from and what time it is in your corner of the world. There's something beautifully fitting about discussing these celestial light shows while we're scattered across different time zones, each of us beneath the same vast sky that occasionally blooms with these ethereal displays. If you find comfort in these soft explorations of scientific wonder, I'd be grateful if you'd consider subscribing. The universe holds countless mysteries, and we have all the time we need to uncover them together, one gentle revelation at a time. So settle in, let your breathing slow, and prepare to discover why the aurora has captivated human imagination for millennia, inspiring everything from ancient myths to modern scientific breakthroughs. Imagine, you're standing in the crisp stillness of an Arctic night, your breath forming small clouds in the frigid air. Above you, the sky begins to shimmer. At first, it's just a faint green glow on the horizon, like the last whisper of a distant sunset. But then, as if awakened by some cosmic conductor, the light begins to move. Ribbons of emerald and gold unfurl across the heavens, twisting and flowing like silk scarves caught in an invisible breeze. The aurora has begun its ancient dance. For thousands of years, humans have gazed up at these celestial light shows with wonder, fear, and reverence. The Inuit peoples of the Arctic believed the aurora was the spirits of their ancestors dancing across the sky, celebrating in the afterlife. Norse mythology told of the Bifrost, the rainbow bridge that connected Earth to Asgard, the realm of the gods. Finnish folklore spoke of the Revontulet, or firefox flames, created by a magical fox running so fast across the snow that its tail swept up flakes into the sky, where they caught fire and glowed. These stories, beautiful as they are, hint at something profound about the human experience. When faced with phenomena we cannot immediately understand, we create narratives that connect us to something greater than ourselves. The aurora, in its ethereal beauty, seems to invite such storytelling. It appears suddenly, without warning, transforms the familiar night sky into something otherworldly, and then vanishes just as mysteriously, leaving observers wondering if they truly witnessed what they thought they saw. But what exactly are we witnessing when we see the aurora? The answer lies in a cosmic conversation that begins 93 million miles away on the surface of our sun. Our star, that reliable source of warmth and light, is far from the steady, unchanging orb it appears to be from Earth. The sun is a roiling, dynamic ball of plasma, constantly erupting with solar flares and coronal mass ejections that send charged particles streaming through space at incredible speeds. This stream of particles, known as the solar wind, carries with it the sun's magnetic field, creating what scientists call the interplanetary magnetic field. As this solar wind races through the solar system at speeds of up to 800 kilometers per second, it encounters the planets in its path. Most planets, lacking strong magnetic fields, are essentially defenseless against this cosmic bombardment. Mars, for instance, has likely lost much of its atmosphere to the solar wind over billions of years. But Earth is different. Our planet possesses something remarkable: a powerful magnetic field generated by the churning of molten iron in our planet's core. This magnetic field, called the magnetosphere, extends far into space, creating an invisible shield that deflects most of the solar wind around our planet. Imagine the magnetosphere as a cosmic umbrella, protecting us from the constant rain of charged particles streaming from the sun. However, this protection isn't perfect. The interaction between the solar wind and Earth's magnetic field is complex and dynamic. When the solar wind encounters our magnetosphere, it compresses it on the day side of Earth and stretches it into a long tail on the night side. Sometimes, particularly during periods of intense solar activity, the solar wind can overwhelm parts of our magnetic defense system. The most dramatic interactions occur when the magnetic field carried by the solar wind aligns in the opposite direction to Earth's magnetic field. When this happens, the magnetic field lines can reconnect in a process called magnetic reconnection. This reconnection acts like a cosmic slingshot, accelerating charged particles from the solar wind toward Earth's upper atmosphere at tremendous speeds. As these energetic particles, primarily electrons and protons, penetrate our magnetosphere, they're guided by Earth's magnetic field lines toward the polar regions. It's here, in the thin upper atmosphere roughly 100 to 300 kilometers above Earth's surface, that the magic happens. The incoming particles collide with atoms and molecules of oxygen and nitrogen in our atmosphere, transferring their energy to these atmospheric gases. When an atom absorbs this energy, its electrons are excited to higher energy levels. But atoms prefer to exist in their lowest energy state, so these excited electrons quickly fall back to their original levels, releasing the excess energy as photons of light. Different atmospheric gases produce different colors when excited. Oxygen, the most abundant gas at aurora altitudes, produces the characteristic green glow we most commonly associate with the aurora. At higher altitudes, oxygen can produce red light, while nitrogen contributes blues and purples to the aurora's palette. The result is a light show of extraordinary beauty and complexity. The aurora's characteristic curtain-like appearance comes from the fact that the charged particles are following Earth's magnetic field lines, which converge at the magnetic poles. These field lines act like invisible highways, guiding the particles downward in roughly parallel paths, creating the vertical structures we see draped across the sky. But the aurora is far from static. The intensity and location of the aurora change constantly in response to variations in the solar wind and Earth's magnetic field. During periods of high solar activity, when the sun releases particularly powerful bursts of particles, the aurora can become so intense that it's visible much farther from the poles than usual. Historical records tell us of aurora displays visible as far south as the Caribbean during particularly severe geomagnetic storms. The aurora also follows predictable patterns related to solar activity. The sun goes through an 11-year cycle of activity, with periods of solar maximum characterized by frequent solar flares and coronal mass ejections, followed by periods of solar minimum when the sun is relatively quiet. During solar maximum, aurora displays become more frequent and intense, while during solar minimum, they're largely confined to the immediate polar regions. Interestingly, the aurora appears simultaneously in both the northern and southern hemispheres, creating mirror images of each other. This happens because the same magnetic field lines that guide particles to the North Pole also extend to the South Pole. When particles follow these field lines, they create aurora displays at both ends, though the exact shapes and intensities can vary due to differences in the magnetic field, geometry, and atmospheric conditions. The study of aurora has revealed much about our planet's magnetic field and its interaction with the solar wind. Scientists have discovered that the aurora is just one visible manifestation of a much larger system of electrical currents and magnetic fields that extends throughout Earth's magnetosphere. These currents, driven by the interaction between the solar wind and Earth's magnetic field, can affect everything from satellite communications to power grids on Earth's surface. Modern technology has allowed us to study the aurora in unprecedented detail. Satellites positioned throughout Earth's magnetosphere monitor the solar wind and track the movement of charged particles. Ground-based instruments measure the magnetic field fluctuations that accompany aurora displays. High-resolution cameras and spectrometers analyze the light emitted by the aurora, revealing details about atmospheric composition and the energy of the incoming particles. Yet for all our scientific understanding, the aurora retains its power to inspire wonder. There's something deeply moving about standing beneath these lights, feeling connected to the cosmic forces that created them. The aurora reminds us that we live on a planet embedded in a dynamic solar system, constantly interacting with the space environment around us. It's a visible reminder of the invisible forces that shape our world and protect us from the harsh environment of space. As you drift towards sleep tonight, perhaps you can imagine yourself standing beneath the aurora, watching as Earth's magnetic field conducts its silent symphony of light. The same magnetic field that creates these beautiful displays also shields us from harmful radiation, allowing life to flourish on our planet. In the gentle glow of the aurora, we can see the cosmos speaking to us in whispers of light, telling the story of our planet's place in the grand theatre of space. The aurora is more than just a pretty light show. It's a window into the fundamental forces that govern our universe. It speaks to the electromagnetic nature of reality, the way matter and energy interact across vast distances, and the delicate balance that makes life possible on our small blue world. Now, as we drift deeper into our cosmic journey, we find ourselves at the gentle edge of discovery, where the night sky whispers secrets that have captivated humanity for millennia. We've traced the birth of stars and watched galaxies dance in their gravitational embrace. But tonight, we turn our attention to something equally extraordinary, yet far more immediate. The shimmering curtains of light that paint Earth's polar skies in colors that seem borrowed from dreams themselves. These are the auroras, those ethereal displays that have inspired countless myths and legends across cultures. The Norse called them the bridge between worlds, while indigenous peoples of the Arctic spoke of dancing spirits playing in the heavens. Modern science has revealed an even more remarkable truth. These lights represent one of the most beautiful examples of our planet's intimate connection to the sun, a cosmic conversation written in photons across the darkness. The story of auroras begins not in our atmosphere, but 93 million miles away in the roiling depths of our nearest star. The sun, that seemingly constant source of warmth and light, is actually a tempestuous ball of plasma where magnetic field lines twist and writhe like cosmic serpents. Occasionally, these magnetic tensions build to a breaking point, releasing enormous bursts of energy that send billions of charged particles streaming through space at speeds approaching 2 million miles per hour. This solar wind, as astronomers call it, carries with it fragments of the sun's own magnetic field. When these particles encounter Earth's protective magnetic envelope, our magnetosphere, something magical happens. Our planet's magnetic field acts like an invisible shield, deflecting most of these charged particles around us, like water flowing around a stone in a stream. But some particles find their way through, particularly near the magnetic poles where the field lines converge and dip closest to our atmosphere. Here, roughly 60 to 200 miles above our heads, these solar visitors collide with molecules of oxygen and nitrogen in our upper atmosphere. The impact excites these atmospheric gases, causing them to emit light in much the same way that electricity flowing through a neon sign creates its characteristic glow. Oxygen, when struck by these cosmic messengers, produces the familiar green curtains that dominate most auroral displays, while higher altitude oxygen creates the rarer red auroras that occasionally grace our skies. Nitrogen contributes its own palette of blues and purples, adding depth and complexity to nature's most spectacular light show. The auroras we see are thus the visible manifestation of our planet's magnetic field at work, protecting us from the sun's more energetic outbursts while creating beauty from what could otherwise be destruction. Each shimmering curtain represents billions of individual collisions between solar particles and atmospheric molecules, a dance of physics that transforms the invisible forces of space into visible poetry across our night sky. These displays follow the contours of Earth's magnetic field, creating two permanent auroral ovals that encircle the magnetic poles. The northern lights, or aurora borealis, crown the Arctic regions, while their southern counterpart, the aurora australis, graces the Antarctic skies. These ovals expand and contract with the intensity of solar activity, occasionally stretching far enough south to be visible from locations as unlikely as the Caribbean, or as far north as to be seen from northern Scotland. The intensity and frequency of auroral displays follow an 11-year cycle that mirrors the sun's own magnetic heartbeat. During solar maximum, when our star's magnetic field is most active and sunspots pepper its surface, auroras become more frequent and intense. Conversely, during solar minimum, these displays retreat to the highest latitudes, becoming rare treats for those patient enough to seek them out in the polar wilderness. But auroras are more than just beautiful lights. They're a window into the invisible forces that shape our cosmic environment. Scientists study these displays to better understand the complex interactions between solar wind and planetary magnetic fields. Knowledge that helps us predict space weather events that can affect satellites, power grids, and communication systems. Each aurora tells a story of magnetic field lines reconnecting, of plasma temperatures and particle densities, of the delicate balance that maintains our planet's protective barrier against the harsh environment of space. The colors we see in auroral displays reveal the very composition of our atmosphere. The predominant green comes from oxygen atoms roughly 100 miles above our heads, while the rare red auroras originate from oxygen at much higher altitudes where the atmosphere is thinner and collisions less frequent. The blues and purples that sometimes accent these displays come from nitrogen molecules, creating a natural spectrometer that allows us to read the chemical signature of our upper atmosphere written in light across the darkness. Recent advances in satellite technology and ground-based observation networks have revealed that auroras are even more complex and beautiful than we once imagined. High-speed cameras capture subtle pulsations and movements invisible to the naked eye, while space-based instruments show us how these displays connect to vast electrical currents flowing through the magnetosphere. We've discovered that auroras can produce radio waves, that they're accompanied by invisible ultraviolet displays, and that they're connected to phenomena occurring thousands of miles above our heads in the outer reaches of Earth's magnetic field. The auroras remind us that our planet is not isolated in space, but intimately connected to the sun and the broader cosmos. Every photon of auroral light represents a successful interaction between our magnetic field and the solar wind, a small victory in the ongoing battle to maintain the protective barrier that makes life possible on Earth. These displays are visible proof that we live on a magnetic planet, one whose invisible field reaches far into space and shapes the very environment that surrounds us. As we continue to study these magnificent displays, we're learning that auroras are not unique to Earth. Other planets with magnetic fields and atmospheres create their own auroral displays. Jupiter's auroras dwarf our own in intensity, while Saturn's polar regions glow with their own ethereal light. Even Mars, with its weak magnetic field, occasionally produces faint auroral displays that remind us of its more magnetically active past. Tonight, as you settle into sleep, imagine the invisible dance taking place high above your head. Solar particles stream through space, carrying with them the magnetic signature of our star. Most are deflected by Earth's protective field, but some find their way through to paint the polar skies with colors that speak to the fundamental forces governing our cosmic neighborhood. In this gentle collision between sun and earth, between the visible and invisible, between the terrestrial and the cosmic, we find one of nature's most beautiful reminders that we are part of something far grander than ourselves. The dance of the auroras begins not with light, but with darkness. In the vast emptiness between earth and sun, an invisible river flows, a stream of charged particles racing through space at speeds that would make our fastest rockets seem stationary. This is the solar wind, and it carries with it the raw materials for one of nature's most spectacular performances. Picture, if you will, our sun as a great cosmic campfire, its nuclear furnace burning at temperatures that defy comprehension. From its surface, a constant breeze emanates, not of air, but of electrons and protons, the fundamental building blocks of matter itself. These particles, energized by the sun's tremendous heat, escape its gravitational embrace and stream outward in all directions, creating an invisible sphere of influence that extends far beyond the orbit of Pluto. This solar wind is not uniform or steady. Like weather patterns on Earth, it varies with the sun's moods and seasons. During periods of solar maximum, when our star's magnetic field lines twist and tangle like cosmic spaghetti, the solar wind intensifies. Massive solar flares erupt from the sun's surface, hurling billions of tons of charged particles into space at velocities approaching 1,000 kilometers per second. Coronal mass ejections, those spectacular explosions of solar plasma, can send shockwaves rippling through the solar system, carrying with them the seeds of auroral displays that will paint Earth's skies in ethereal colors. But the journey from sun to Earth is not a simple straight line. The solar wind carries within it the sun's magnetic field, frozen into the plasma like invisible threads of force. This interplanetary magnetic field spirals outward from the sun, creating a vast magnetic structure that fills our solar system. When this field encounters Earth's own magnetic cocoon, our magnetosphere, the stage is set for the cosmic dance that creates the auroras. Earth's magnetosphere is our planet's invisible shield, a bubble of magnetic force that extends tens of thousands of kilometers into space. Generated by the churning motion of molten iron in our planet's core, this magnetic field acts as a protective barrier, deflecting most of the solar wind around our world like water flowing around a stone in a stream. Without this shield, the solar wind would strip away our atmosphere over millions of years, leaving Earth as barren as Mars. Yet the magnetosphere is not an impermeable fortress. It has weak points, particularly at the magnetic poles, where the field lines converge and dip down toward the planet's surface. Here, the solar wind can penetrate deeper into our magnetic domain, following the curved pathways of Earth's magnetic field like cars following the lanes of a cosmic highway. As these charged particles spiral down along the magnetic field lines, they encounter the upper reaches of our atmosphere, and it is here that the magic truly begins. The atmosphere that surrounds our planet is layered like an onion, each shell with its own character and composition. In the thermosphere, roughly 80 to 400 kilometers above the surface, the air is thin beyond imagination, so sparse that a handful of this high-altitude atmosphere would contain fewer molecules than a single breath at sea level. Yet it is dense enough to interact with the incoming solar particles, and when these cosmic visitors collide with atmospheric gases, they transfer their energy in the most beautiful way possible. The process is surprisingly similar to what happens inside a neon sign. When the solar wind particles, primarily electrons and protons, collide with atoms of oxygen and nitrogen in the upper atmosphere, they impart their energy to these atmospheric residents. The oxygen and nitrogen atoms become excited, their electrons jumping to higher energy levels like dancers leaping onto a stage. But this excited state is temporary and unstable. Within fractions of a second, the electrons fall back to their original energy levels, releasing the excess energy as photons of light. The color of this light depends on which atmospheric gas is involved and at what altitude the interaction occurs. Oxygen atoms, when struck by solar particles at altitudes between 100 and 300 kilometers, emit a brilliant green light, the signature color of most auroral displays. This green glow is so distinctive that it has become synonymous with the northern lights themselves. At higher altitudes, above 300 kilometers, oxygen produces a deep red light, creating the crimson curtains that sometimes crown the most spectacular auroral displays. Nitrogen contributes its own palette to the auroral spectrum. At lower altitudes, nitrogen molecules emit a rich blue light, while at higher elevations they produce a purple glow. Sometimes, when conditions are just right, all these colors blend together in a symphony of light that spans the entire visible spectrum, creating auroras that shift and dance through every hue imaginable. The intensity and extent of these displays depend on the strength of the solar wind and the orientation of its magnetic field. When the interplanetary magnetic field carried by the solar wind aligns in a particular way with Earth's magnetic field, specifically when it points southward, a process called magnetic reconnection occurs. This is perhaps the most crucial mechanism in auroral formation, yet it remains invisible to our eyes, playing out in the realm of plasma physics and electromagnetic forces. During magnetic reconnection, the magnetic field lines of the solar wind and Earth's magnetosphere link up and merge, creating new pathways for charged particles to enter our magnetic domain. It's as if cosmic doors suddenly swing open, allowing the solar wind to penetrate much deeper into the magnetosphere than would normally be possible. These reconnection events can occur on the day side of Earth, where the solar wind first encounters our magnetic field, but they also happen on the night side, in the long magnetic tail that streams away from our planet like a comet's tail. The particles that enter Earth's magnetosphere during these events don't immediately create auroras. Instead, they become trapped in the complex magnetic geometry of our planet's field, bouncing back and forth between the magnetic poles like cosmic pinballs. Some particles are stored in regions called the Van Allen radiation belts, great toroids of trapped charged particles that encircle our planet. Others are accelerated by magnetic processes and electric fields, gaining energy as they spiral through the magnetosphere. Eventually, these energized particles find their way to the auroral zones, oval-shaped regions centered on each magnetic pole, where the magnetic field lines provide the most direct pathways to the upper atmosphere. As night falls and the sky darkens, the stage is set for the auroral performance to begin. The first hints often appear as a faint green glow on the northern horizon, like the distant lights of a city just beyond the curve of the Earth. But as more particles stream down from the magnetosphere, the display intensifies and evolves. Vertical curtains of light begin to form, following the invisible magnetic field lines that guide the particles earthward. These curtains can stretch for hundreds of kilometers across the sky, yet they may be only a few hundred meters thick. Vast, ethereal sheets of light that seem to hang in the darkness like cosmic theater curtains. The auroras are not static. They are constantly in motion, responding to the ever-changing conditions in the magnetosphere far above. As the solar wind varies in strength and direction, as magnetic reconnection events occur and subside, the auroral displays shift and dance accordingly. Curtains of light may suddenly brighten and spread across the sky, or they may fade to a barely perceptible glow before flaring back to life. The lights can move with surprising speed, racing across the heavens in waves and spirals that seem to follow some celestial choreography. Scientists have discovered that these movements are not random, but follow the patterns of electric currents and magnetic field disturbances in the magnetosphere. The auroras are, in essence, a visual representation of the invisible electromagnetic processes occurring hundreds of kilometers above our heads. They are nature's way of making the invisible visible, transforming the abstract concepts of plasma physics into a display of light and color that can move us to tears. The auroral oval, as scientists call the ring-shaped region where auroras most commonly occur, is not fixed in place, but moves and changes with the level of magnetic activity. During quiet periods, when the solar wind is gentle and steady, the auroral oval contracts toward the poles, and the lights may be visible only from the most northern and southern latitudes. But during magnetic storms, when the solar wind is particularly strong, or when large coronal mass ejections interact with Earth's magnetosphere, the auroral oval expands dramatically. It is during these geomagnetic storms that the auroras become visible at much lower latitudes, sometimes appearing as far south as the northern United States, or even further. Historical records tell of auroral displays visible from Rome and the Mediterranean during particularly intense magnetic storms. These events, while beautiful, are also signs of significant disturbances in near-Earth space that can affect satellite communications, GPS navigation, and even power grids on the ground. The relationship between solar activity and auroral frequency follows an 11-year cycle that mirrors the Sun's magnetic activity cycle. During solar maximum, when the Sun's magnetic field is most tangled and active, coronal mass ejections and solar flares are more frequent and intense, leading to more numerous and spectacular auroral displays. Conversely, during solar minimum, auroral activity decreases, and the lights may be visible only from the highest latitudes. This connection between solar activity and terrestrial auroras reveals the intimate relationship between Earth and its parent star. We are not isolated in space, but connected to the Sun by invisible threads of magnetic force and streams of charged particles. The auroras are a constant reminder of this connection, a visual manifestation of the space weather that flows between the worlds of our solar system. The particles that create the auroras complete their journey from Sun to Earth in a matter of days, but the light they produce when they finally interact with our atmosphere lasts only moments. Each photon of auroral light represents the end of an epic journey, a charged particle that was born in the nuclear furnace of the Sun, accelerated by magnetic fields, carried across 93 million miles of space, captured by Earth's magnetosphere, and finally brought to rest in a collision with an atmospheric atom that transforms its kinetic energy into a brief flash of colored light. Yet even as individual photons fade, the auroral display continues, sustained by the constant stream of particles flowing from the Sun. The aurora is thus both ephemeral and eternal. Each moment of light is fleeting, but the overall phenomenon has been occurring for as long as Earth has possessed both an atmosphere and a magnetic field. Rocks from billions of years ago contain magnetic signatures that suggest our planet's magnetic field has existed for most of Earth's history, which means the auroras have been painting the skies for eons, long before there were any eyes to witness their beauty. The auroras we see today are the same phenomena that amazed our ancestors, yet our scientific understanding has transformed them from mysterious omens into windows into the workings of our planet's magnetic environment. They are simultaneously ancient and immediate, cosmic and terrestrial, simple in their basic mechanism, yet infinitely complex in their detailed behavior. In their dancing lights, we can read the story of our Sun's moods, our planet's magnetic personality, and the invisible forces that shape the space around our world. As we continue to study these phenomena with ever more sophisticated instruments, from ground-based cameras and magnetometers to spacecraft positioned throughout the magnetosphere, we are still discovering new aspects of auroral physics. The auroras remain a frontier of scientific research. a natural laboratory where we can study plasma physics, magnetic reconnection, and the interaction between solar wind and planetary magnetic fields. As we've journeyed through the cosmic origins of auroras and witnessed their ethereal dance across polar skies, we now turn our attention to something equally fascinating, yet profoundly more intimate. The aurora isn't just a distant light show playing out in the upper atmosphere. It's a living, breathing phenomenon that responds to the heartbeat of our solar system itself. Every pulse of solar wind, every magnetic field line that snaps and reconnects, every particle that spirals down through Earth's protective magnetic embrace contributes to this most elegant of cosmic conversations. Picture yourself standing beneath the aurora on a crystal-clear Arctic night. The silence is almost tangible, broken only by the gentle whisper of wind across the tundra. Above you, curtains of light begin their slow, hypnotic dance, flowing like silk scarves caught in a celestial breeze. But here's what makes this moment truly extraordinary. What you're witnessing isn't just beautiful, it's intelligent. The aurora is Earth's way of speaking, of translating the invisible language of space weather into something we can see, something that touches our very souls. The magnetic field lines that guide these charged particles aren't rigid highways carved in stone. They're dynamic, living structures that pulse and breathe with the rhythm of our planet's magnetic heart. Deep beneath your feet, thousands of kilometers down in Earth's molten core, liquid iron swirls in patterns so complex, they make the most sophisticated computer models look like children's drawings. These currents generate the magnetic field that reaches far into space, creating our magnetosphere, that invisible shield that makes life on Earth possible. But here's where the story becomes truly remarkable. The solar wind isn't just a steady stream of particles flowing from the sun. It's a turbulent river of plasma, carrying with it the magnetic personality of our star. When this solar wind encounters Earth's magnetic field, something magical happens. The two magnetic fields, one from Earth and one from the sun, begin a cosmic dance of connection and disconnection, of tension and release, of build-up and explosive reconnection. This process, called magnetic reconnection, is perhaps one of the most elegant phenomena in all of physics. Imagine two rivers flowing toward each other, each carrying its own current and character. When they meet, they don't simply bounce off each other. Instead, they merge, exchange energy, and create something entirely new. The magnetic field lines from the sun connect with Earth's magnetic field lines, creating pathways that allow solar particles to flow into our magnetosphere like invited guests entering a grand ballroom. These particles, once they've gained entry through magnetic reconnection, don't simply plummet straight down toward Earth. Instead, they follow the graceful curves of our planet's magnetic field lines, spiraling and dancing as they make their way toward the polar regions. It's a journey that can take hours or even days, as particles drift through different regions of the magnetosphere, each with its own unique character and behavior. The magnetosphere itself is a wonderland of plasma physics, with regions that have names as poetic as the phenomena they describe. There's the plasmasphere, a torus of cold, dense plasma that rotates with Earth like a loyal companion. There's the radiation belts, discovered by Explorer 1 in 1958, where energetic particles bounce back and forth between Earth's magnetic poles in a cosmic game of pinball. And there's the magnetotail, a long comet-like extension of Earth's magnetic field that stretches far into space on the night side of our planet. Each of these regions plays a role in the aurora story. Particles can be stored in the magnetotail for hours or days, slowly building up energy like water behind a dam. When conditions are right, when the solar wind pressure changes, or when magnetic reconnection occurs in the magnetotail, these stored particles are suddenly released, racing toward Earth along magnetic field lines with tremendous speed and energy. As these particles approach Earth's atmosphere, they encounter the first wisps of our planet's gaseous envelope at altitudes of several hundred kilometers. Here, the air is so thin it's almost like being in space, but it's thick enough to begin interacting with the incoming charged particles. The particles, moving at speeds of hundreds of kilometers per second, begin to collide with oxygen and nitrogen molecules, transferring their energy in a process that's both violent and beautiful. The collision itself is a quantum mechanical marvel. When a high-energy electron strikes an oxygen atom, it doesn't simply bounce off like a billiard ball. Instead, it transfers its energy to the oxygen atom, exciting one of the atom's electrons to a higher energy state. This is an unstable situation. Nature abhors it, and the excited electron quickly falls back to its ground state, releasing the extra energy as a photon of light. The color of that light depends on which energy levels are involved in the transition and which gas is being excited. Oxygen, that life-giving element that fills our lungs with every breath, creates the aurora's most characteristic colors. At altitudes around 200 to 300 kilometers, where the aurora is most commonly seen, oxygen produces that stunning green light that's become synonymous with the northern lights. It's a color so pure, so vivid, that it seems almost artificial, like nature's own neon sign painted across the sky. But oxygen has another trick up its sleeve. At higher altitudes, where the air is even thinner and collisions are less frequent, oxygen can produce a deep red light. This red aurora is less common but equally spectacular, often appearing as a faint glow along the upper edges of the green aurora, like a cosmic blush painting the highest reaches of our atmosphere. Nitrogen, the gas that makes up most of our atmosphere, contributes its own colors to the aurora palette. It can produce brilliant blues and purples, often appearing as rapid flickering lights that dance at the lower edges of the aurora display. These colors are typically seen at lower altitudes, where the atmosphere is slightly denser and nitrogen is more abundant. The altitude at which these collisions occur is crucial to understanding the aurora's appearance. The atmosphere changes dramatically with height, becoming thinner and thinner as you move away from Earth's surface. At the altitudes where auroras occur, the air is so thin that an aurora photon, once created, can travel for kilometers without being absorbed or scattered. This is why aurora displays can appear so sharp and well-defined, with curtains of light that seem to hang in space like luminous fabric. But the aurora isn't just about individual particles colliding with individual atoms. It's about vast sheets of electrical current flowing through the upper atmosphere, creating electromagnetic fields that can be detected on Earth's surface. These currents, driven by the solar wind and guided by Earth's magnetic field, can be so strong that they interfere with radio communications, disrupt satellite operations, and even affect power grids on the ground. The aurora is also remarkably dynamic, changing its appearance minute by minute, sometimes second by second. The curtains of light can wave and ripple like flags in the wind. They can pulse and flicker like cosmic heartbeats, and they can suddenly brighten or fade as the flow of particles from space changes. This dynamic behavior reflects the constantly changing conditions in the solar wind and in Earth's magnetosphere. One of the most spectacular aurora phenomena is the substorm, a process that can suddenly brighten the aurora and cause it to dance with incredible speed and complexity. Substorms occur when energy that has been slowly building up in the magnetotail is suddenly released, like a rubber band snapping back to its original shape. The released energy accelerates particles toward Earth, creating brilliant displays that can fill the entire sky with moving light. These substorms follow a predictable pattern with distinct phases that aurora researchers have studied for decades. There's the growth phase, when energy slowly builds up in the magnetotail. Then comes the expansion phase, when the stored energy is suddenly released and the aurora explodes into activity. Finally, there's the recovery phase, when the system slowly returns to its quiet state, ready for the next cycle. The beauty of aurora science lies in how it connects the largest scales of our solar system with the smallest scales of atomic physics. A solar flare that occurs on the Sun, 150 million kilometers away, can trigger a geomagnetic storm that produces auroras visible from space. The magnetic field lines that guide particles from the solar wind to Earth's atmosphere stretch across millions of kilometers. Yet the actual light we see is produced by quantum transitions in individual atoms. This connection between the cosmic and the microscopic is what makes the aurora so scientifically fascinating and so deeply moving to witness. When you stand beneath the aurora, you're not just seeing a pretty light show. You're witnessing the direct connection between Earth and space, between our planet and our star, between the smallest particles and the largest magnetic fields in our solar system. The aurora also serves as a natural laboratory for studying plasma physics, the science of ionized gases that make up 99% of the visible universe. The processes that create auroras on Earth are similar to those that occur in the atmospheres of other planets, in the solar wind, and even in distant stars and galaxies. By studying auroras, we learn about fundamental processes that operate throughout the universe. As we continue to explore the aurora phenomenon, we're constantly discovering new aspects of this cosmic light show. High-resolution cameras and sensitive instruments have revealed fine structures in the aurora that were invisible to earlier observers. We've discovered that the aurora can produce its own sounds, faint crackling or hissing noises that occur when the electromagnetic fields associated with the aurora interact with objects on the ground. We've also learned that the aurora is just one manifestation of a much larger system of currents and fields that connect Earth's upper atmosphere to the solar wind. The aurora is the visible tip of an invisible iceberg of electromagnetic activity that extends from Earth's surface to the edge of the solar system. The more we study the aurora, the more we realize how perfectly it embodies the interconnectedness of our solar system. It's a phenomenon that requires the sun, the solar wind, Earth's magnetic field, and our planet's atmosphere to all work together in perfect harmony. Change any one of these components, and the aurora would look completely different or might not exist at all. This interconnectedness extends to life on Earth as well. The same magnetic field that creates the aurora also protects us from harmful cosmic radiation. The same solar wind that powers the aurora also drives space weather that can affect our technology and our daily lives. The aurora is both a beautiful natural phenomenon and a reminder of our planet's place in the larger cosmic environment. As we stand beneath the aurora, watching its ethereal dance across the polar sky, we're witnessing one of nature's most perfect examples of invisible forces made visible, of cosmic processes translated into earthly beauty. The aurora whispers to us in the language of light, telling us stories of magnetic fields and solar winds, of quantum transitions and electromagnetic currents, of the deep connections that bind our planet to the cosmos. In the aurora's gentle glow, we find not just beauty, but truth. The truth that we are part of something much larger than ourselves, that our planet is intimately connected to the sun and stars, and that the same physical laws that govern the smallest atoms also guide the largest structures in the universe. Looking at the magnetic canvas of our polar skies, we encounter phenomena that serve as Earth's most eloquent translators, converting the invisible language of solar radiation into visual poetry that has captivated humanity for millennia. The auroras represent far more than mere atmospheric light shows. They are the visible manifestation of our planet's magnetic heartbeat, pulsing in rhythm with the solar wind that streams across the vacuum of space. The relationship between Earth and Sun creates a dynamic interplay of forces that culminates in these ethereal displays. When the solar wind, that ceaseless stream of charged particles flowing from our star at speeds exceeding 1 million miles per hour, encounters Earth's magnetosphere, it initiates a complex choreography of electromagnetic interactions. The magnetosphere, our planet's invisible magnetic shield extending thousands of miles into space, acts as both protector and conductor, channeling these solar particles toward the polar regions where they can safely interact with our atmosphere. This channeling process represents one of nature's most elegant solutions to a cosmic challenge. Rather than allowing the solar wind to bombard our planet's surface directly, potentially stripping away our atmosphere as has occurred on Mars, Earth's magnetic field creates a protective bubble that deflects most of these particles, while capturing and redirecting a controlled portion towards the magnetic poles. The result is a system that transforms potential destruction into breathtaking beauty. The actual creation of auroral light occurs when these magnetically guided particles collide with gases in our upper atmosphere, primarily oxygen and nitrogen. These collisions occur at altitudes between 50 and 300 miles above Earth's surface, in the rarefied realm where our atmosphere gradually transitions into the vacuum of space. When a charged particle from the solar wind strikes an oxygen or nitrogen molecule, it transfers energy to that molecule, causing it to become excited and emit light as it returns to its ground state. The colors we observe in auroras result from the specific types of atmospheric gases being excited and the altitudes at which these interactions occur. The most common auroral color, that familiar green glow that dominates so many photographs, comes from oxygen atoms being excited at altitudes around 60 to 100 miles above Earth. At higher altitudes, typically above 150 miles, oxygen produces a rarer red emission, creating the crimson curtains that sometimes crown the green displays. Nitrogen contributes blue and purple hues, often appearing as delicate fringes along the edges of auroral formations, or as the primary color in intense displays. These interactions create more than just static glows. They produce dynamic, ever-changing patterns that can shift from gentle undulations to explosive bursts of activity within seconds. The aurora's characteristic curtain-like appearance results from the way Earth's magnetic field lines guide the charged particles downward. These invisible magnetic highways create vertical sheets of luminosity that can extend hundreds of miles across the sky while maintaining relatively narrow thickness, typically just a few hundred yards wide despite their vast scale. The timing and intensity of auroral displays follow the rhythm of solar activity, which operates on an approximately 11-year cycle. During periods of solar maximum, when our star's magnetic field is most active and unstable, solar flares and coronal mass ejections become more frequent and powerful. These events can overwhelm Earth's magnetic defenses, allowing auroral displays to extend far beyond their usual polar confines and reach latitudes where they can be observed by much larger populations. During particularly intense geomagnetic storms, auroras have been observed as far south as the Caribbean and as far north as regions where they are normally invisible due to the extreme tilt of Earth's magnetic field. These rare events serve as reminders of our planet's connection to solar processes and the delicate balance that normally confines these displays to the polar regions. The expansion of the auroral oval during these storms creates opportunities for millions of additional people to witness these phenomena, often leading to widespread reports of unusual lights in the sky. The study of auroras has contributed significantly to our understanding of plasma physics and the behavior of charged particles in magnetic fields. The Earth-Sun system essentially operates as a vast natural laboratory where we can observe electromagnetic processes that would be impossible to recreate artificially. The way charged particles spiral along magnetic field lines, the manner in which magnetic reconnection releases stored energy, and the complex feedback loops between solar wind conditions and terrestrial magnetic responses all provide insights into fundamental physical processes that operate throughout the universe. Modern technology has revealed that auroral activity extends far beyond the visible spectrum. Radio waves generated by auroral processes can be detected by specialized equipment, creating an acoustic dimension to these displays. The interaction between charged particles and Earth's magnetic field generates electromagnetic noise that can be converted into audio frequencies, producing sounds that range from gentle whispers to explosive crashes. These auroral sounds, while not audible to the human ear without electronic assistance, add another layer of complexity to our understanding of these phenomena. The global nature of auroral activity becomes apparent when viewed from space, where satellites and astronauts can observe the complete auroral oval that encircles each magnetic pole. These space-based observations reveal that auroras occur simultaneously in both hemispheres, creating mirror image displays that are connected by the same magnetic field lines. When a bright aurora appears over northern Canada, a corresponding display typically illuminates the skies over Antarctica, demonstrating the truly global nature of these electromagnetic processes. The influence of auroral activity extends beyond mere spectacle to impact technological systems that modern society depends upon. The same charged particles that create beautiful lights in the sky can interfere with radio communications, disrupt satellite operations, and even induce electrical currents in power grids. Major geomagnetic storms have caused widespread blackouts, damaged transformers, and interrupted global communication systems, highlighting the practical importance of understanding and predicting auroral activity. Scientists have developed sophisticated models to forecast auroral activity, combining real-time solar observations with detailed understanding of Earth's magnetic field behavior. These predictions help protect sensitive technological systems, while also allowing aurora enthusiasts to plan viewing opportunities. The ability to predict when and where auroras will appear represents a remarkable achievement in space weather science, demonstrating how fundamental research into beautiful natural phenomena can yield practical benefits for society. The cultural significance of auroras extends across virtually every civilization that has had the opportunity to observe them regularly. Indigenous peoples of the Arctic regions have developed rich mythological traditions surrounding these displays, often interpreting them as spirits of the departed, dancing lights of the gods, or bridges between the earthly and celestial realms. These cultural interpretations, while scientifically inaccurate, capture something profound about the emotional and spiritual impact of witnessing auroral displays. Contemporary understanding of auroras as electromagnetic phenomena in no way diminishes their capacity to inspire wonder and contemplation. If anything, knowledge of the vast scales and complex processes involved in their creation enhances their significance. Each auroral display represents a moment when the normally invisible relationship between Earth and Sun becomes visible, when the abstract concept of magnetic fields transforms into tangible beauty, and when the immensity of space reveals itself through delicate curtains of light dancing across our local sky. The study of auroras continues to evolve with new technologies and theoretical frameworks. Advanced imaging systems can now capture auroral activity across multiple wavelengths simultaneously, revealing structures and processes that were previously invisible. Sophisticated computer models can simulate the complex interactions between solar wind and magnetosphere with increasing accuracy, helping scientists understand not only how auroras form, but how they might behave under different conditions. As we continue to explore the cosmos and discover other worlds with magnetic fields and atmospheres, the knowledge gained from studying Earth's auroras becomes even more valuable. Similar phenomena likely occur on other planets throughout the universe, and understanding the fundamental processes that create auroral displays on Earth provides a foundation for interpreting observations from distant worlds. The auroras that grace our polar skies thus serve as both local treasures and universal keys to understanding electromagnetic processes throughout the cosmos. The next time you witness an aurora, whether in person or through the countless images and videos that capture their beauty, remember that you are observing one of nature's most sophisticated displays of electromagnetic artistry. These lights represent the visible manifestation of invisible forces, the transformation of solar energy into terrestrial beauty, and the ongoing conversation between our planet and its star. The auroras represent one of Earth's most captivating natural phenomena, yet their beauty masks a complex and ongoing scientific mystery. These shimmering curtains of light dancing across polar skies are far more than mere spectacle. They serve as visible manifestations of invisible cosmic forces that constantly shape our planet's relationship with space itself. Recent advances in aurora research have revealed that these celestial displays operate according to principles far more intricate than previously understood. What appears to be a simple interaction between solar particles and Earth's atmosphere actually involves a sophisticated interplay of magnetic field dynamics, plasma physics, and atmospheric chemistry that continues to challenge our fundamental understanding of how planetary systems interact with their stellar environment. The mechanism behind auroral formation begins not on Earth, but in the turbulent outer atmosphere of our Sun. Solar flares and coronal mass ejections launch billions of charged particles into space, creating what scientists call the solar wind. This invisible stream of plasma travels at speeds exceeding 1 million miles per hour, carrying with it the Sun's magnetic field embedded within the particle flow. When this magnetized plasma encounters Earth's protective magnetic bubble, the magnetosphere, it triggers a cascade of events that ultimately manifests as the aurora. Yet the relationship between solar activity and auroral displays is not straightforward. The intensity and frequency of auroras follow an 11-year cycle that corresponds to the Sun's magnetic field reversals. But within this broader pattern lies a wealth of variation that scientists are still working to decode. Some of the most spectacular auroral displays occur not during periods of maximum solar activity, but during specific configurations of the solar wind that create optimal conditions for magnetic reconnection events. This magnetic reconnection process represents one of the most fundamental yet mysterious phenomena in plasma physics. When the Sun's magnetic field, carried by the solar wind, encounters Earth's magnetic field with the proper orientation, the two field lines can suddenly snap together and reorganize themselves in a violent release of energy. This process, which occurs hundreds of thousands of miles above Earth's surface, sends charged particles cascading down magnetic field lines toward the polar regions, where they collide with atmospheric gases to create the aurora. The colors we observe in auroral displays tell a story of atmospheric composition and energy transfer. The familiar green glow that dominates most aurora photographs results from oxygen atoms being excited at altitudes around 100 kilometers above Earth's surface. Higher in the atmosphere, at altitudes above 200 kilometers, oxygen produces a rarer red emission, while nitrogen contributes blues and purples at various altitudes. These color variations reflect not just the types of atmospheric gases present, but also the energy levels of the incoming particles and the density of the atmosphere at different heights. Perhaps most intriguingly, modern research has revealed that auroras are not merely passive displays of incoming solar energy, but active participants in the complex electromagnetic environment surrounding Earth. The same processes that create visible auroras also generate radio waves, accelerate particles to extremely high energies, and create electrical currents that flow through the upper atmosphere and into space. These auroral currents can be so intense that they interfere with satellite operations, disrupt radio communications, and even affect power grids on Earth's surface. The study of auroras has also opened windows into understanding similar phenomena throughout the universe. Every planet in our solar system with a significant magnetic field displays its own version of auroras, from the massive auroral ovals of Jupiter powered by volcanic emissions from its moon Io, to the peculiar auroras of Uranus that result from its tilted magnetic field. These planetary comparisons help scientists understand which aspects of auroral physics are universal and which are unique to Earth's particular electromagnetic environment. Climate scientists have discovered that auroral activity serves as a sensitive indicator of long-term changes in Earth's magnetic field and upper atmospheric conditions. Historical records of auroral sightings, some dating back over 1,000 years, provide valuable data about past solar activity and its effects on Earth's climate system. These records suggest that periods of reduced solar activity, marked by fewer and weaker auroras, may correlate with cooler global temperatures, though the exact mechanisms linking solar variability to climate remain an active area of research. Modern space-based observations have revealed that auroral processes extend far beyond the visible displays we observe from Earth's surface. Spacecraft orbiting in Earth's magnetosphere have detected auroral radio emissions, measured the particle populations responsible for auroral displays, and mapped the three-dimensional structure of the magnetic field configurations that guide auroral particles toward Earth. These observations have shown that the magnetosphere itself pulses and breathes in response to solar wind variations, creating a dynamic environment where auroral activity can change dramatically within minutes or even seconds. The technological implications of aurora research extend well beyond academic curiosity. As human civilization becomes increasingly dependent on satellite communications, GPS navigation, and electrical power grids, understanding and predicting auroral activity becomes crucial for maintaining these systems. Space weather forecasting, which attempts to predict when solar activity will trigger intense auroral displays, has become as important for certain industries as terrestrial weather prediction. Recent discoveries have also revealed previously unknown types of auroral phenomena. Citizen scientists using digital cameras have documented new auroral forms, with names like Steve, Dunes, and picket fence auroras, each representing different physical processes in the upper atmosphere. These discoveries demonstrate that despite centuries of aurora observations, we are still uncovering new aspects of these phenomena that challenge existing theoretical models. The connection between auroras and Earth's magnetic field has taken on new significance as scientists have discovered that our planet's magnetic field is not as stable as once believed. The magnetic North Pole is currently migrating at an accelerating rate, and geological evidence suggests that Earth's magnetic field has reversed its polarity many times throughout planetary history. Understanding how these changes affect auroral patterns provides insights into the potential impacts of future magnetic field variations on both natural systems and human technology. As research continues to unveil the mysteries of auroral phenomena, these dancing lights in the polar skies remain powerful reminders of Earth's place within the dynamic, interconnected system of electromagnetic forces that permeate our solar system and beyond. The Aurora Chronicles, Part 7, The Cosmic Symphony. Picture yourself standing on a remote Arctic hillside, far from the warm glow of civilization, where the night sky stretches endlessly above you like a vast canvas of possibility. The temperature hovers around -30 degrees, and your breath creates small clouds that drift upward into the crystalline air. You've been waiting here for hours, scanning the northern horizon with the patient dedication of someone who understands that nature's most magnificent performances cannot be rushed or commanded. Then it begins. A faint green glow emerges along the horizon, so subtle at first that you wonder if your eyes are playing tricks on you. But within moments, this ethereal light begins to dance, stretching upward like ghostly fingers reaching toward the stars. The aurora borealis has arrived, transforming the night sky into a living, breathing work of art that seems to pulse with the very heartbeat of the planet itself. What you're witnessing is nothing short of miraculous. High above your head, roughly 100 kilometers into the atmosphere, charged particles from the sun are colliding with oxygen and nitrogen atoms in a cosmic ballet that has been playing out for billions of years. Each collision releases a photon of light, and when billions of these collisions occur simultaneously, they create the shimmering curtains of color that now dance across the sky above you. But here's what makes this moment truly extraordinary. You're not just watching a light show. You're observing the visible manifestation of our planet's magnetic field at work. A protective shield that has been safeguarding Earth's atmosphere and making life possible for eons. The aurora is nature's way of showing us something that would otherwise remain completely invisible, a phenomenon so fundamental to our existence that without it, our world would be as barren and lifeless as Mars. The science behind what you're witnessing begins 93 million miles away on the surface of our sun. There, in the roiling chaos of stellar plasma, magnetic field lines twist and writhe like serpents made of pure energy. When these field lines become too tangled and stressed, they snap apart in violent explosions called solar flares, releasing enormous amounts of energy and hurling billions of charged particles into space at speeds that stagger the imagination. This stream of particles, known as the solar wind, races across the void of space at velocities approaching 1,000,000 miles per hour. It carries with it the magnetic signature of our sun, creating what scientists call the interplanetary magnetic field. This invisible river of charged particles flows constantly from the sun, bathing our entire solar system in a sea of electromagnetic energy that would be lethal to unprotected life. As this torrent of solar particles approaches Earth, it encounters our planet's magnetic field, an invisible fortress generated by the churning motion of molten iron in our planet's core. This magnetic field extends far into space, creating a protective bubble called the magnetosphere that deflects most of the solar wind around our planet, like water flowing around a stone in a stream. But the interaction between the solar wind and Earth's magnetic field is far more complex and dynamic than this simple analogy suggests. When the magnetic field, carried by the solar wind, points in the opposite direction to Earth's magnetic field, something remarkable happens. The two magnetic fields can merge and reconnect in a process that scientists call magnetic reconnection, creating temporary doorways through which solar particles can enter our magnetosphere. This process is like watching two rivers merge, except these rivers are made of invisible magnetic energy and charged particles. When reconnection occurs, it releases enormous amounts of energy, accelerating particles to incredible speeds and directing them toward Earth's polar regions along the curved pathways of our planet's magnetic field lines. The particles that successfully penetrate our magnetosphere don't simply rain down randomly onto Earth's atmosphere. Instead, they follow the invisible highways of our magnetic field, spiraling along field lines that funnel them toward the north and south magnetic poles. This is why auroras appear in oval-shaped regions around the magnetic poles, areas that scientists call the auroral ovals. As these high-energy particles slam into the thin atmosphere at altitudes between 80 and 600 kilometers above Earth's surface, they transfer their energy to the atoms and molecules they encounter. Oxygen atoms, when struck by these particles, emit light in characteristic colors: green at lower altitudes and red at higher altitudes. Nitrogen produces blues and purples, creating the full spectrum of auroral colors that paint the night sky. The altitude at which these collisions occur determines not only the color of the aurora, but also its intensity and structure. Lower altitude auroras, occurring between 80 and 150 kilometers above the surface, tend to be brighter and more defined because the atmosphere is denser at these levels. Higher altitude auroras, extending up to 600 kilometers or more, are often more diffuse and ethereal, creating those ghostly red curtains that occasionally stretch across the entire sky. The intensity of the aurora you're witnessing depends on several factors, but the most important is the strength and orientation of the magnetic field carried by the solar wind. When this field aligns in opposition to Earth's magnetic field, the conditions become perfect for strong magnetic reconnection, allowing vast numbers of particles to enter the magnetosphere and create brilliant displays that can be seen even from space. During periods of intense solar activity, when our sun hurls particularly energetic bursts of particles toward Earth, the auroral ovals can expand dramatically. What are normally confined to the Arctic and Antarctic regions can suddenly appear at much lower latitudes, bringing the northern lights to places where they're rarely seen. Historical records tell us of auroras appearing as far south as Rome and the Caribbean during the most powerful solar storms. The aurora you're watching is also a real-time indicator of space weather conditions throughout our solar system. The intensity, color, and movement of the lights above you reflect the current state of the solar wind, the strength of our planet's magnetic field, and the complex interactions occurring in the magnetosphere high above. Scientists use ground-based cameras, satellites, and other instruments to monitor auroral activity as a way of understanding and predicting space weather events that could affect our technology-dependent civilization. Modern auroral research has revealed that the magnetosphere is far more complex than early scientists imagined. It's not simply a static bubble protecting Earth from the solar wind, but rather a dynamic system that constantly changes in response to solar activity. The magnetosphere has a long tail that extends far beyond Earth's night side, and this magnetotail plays a crucial role in storing and releasing the energy that powers auroral displays. During periods of intense solar activity, energy builds up in the magnetotail like water behind a dam. Eventually, this energy is released in explosive events called magnetospheric substorms, which can cause auroras to suddenly brighten and begin dancing across the sky with increased vigor. These substorms can last for several hours and create some of the most spectacular auroral displays on Earth. The solar wind itself is not constant, but varies dramatically depending on conditions on the sun. During solar minimum, when our star is relatively quiet, the solar wind flows steadily but gently, creating modest auroral displays confined mostly to the polar regions. But during solar maximum, when the sun's magnetic field is most chaotic and active, powerful solar storms can hurl massive clouds of particles toward Earth, creating auroral displays of extraordinary beauty and intensity. One of the most fascinating aspects of auroral science is the discovery that Earth's aurora is part of a much larger phenomenon that occurs throughout our solar system. Jupiter, with its powerful magnetic field, hosts auroras that are far more intense than anything seen on Earth. These Jovian auroras are powered not only by the solar wind, but also by volcanic activity on Jupiter's moon Io, which constantly spews charged particles into Jupiter's magnetosphere. Saturn, too, has its own auroral displays, and interestingly, these auroras are closely linked to the planet's mysterious radio emissions. The rotation of Saturn's magnetic field creates a rhythm that powers both the planet's radio signals and its auroral activity, creating a kind of cosmic symphony that scientists are still working to understand. Even planets without strong magnetic fields, like Venus and Mars, experience auroral phenomena, though these are quite different from Earth's auroras. On Mars, localized magnetic fields in the planet's crust can create small-scale auroral displays, while Venus experiences a type of aurora caused by the direct interaction of the solar wind with the planet's atmosphere. The study of auroras has also provided crucial insights into the physics of plasma, the fourth state of matter that makes up the solar wind and much of the visible universe. The magnetosphere acts like a natural laboratory where scientists can study how charged particles behave under extreme conditions, advancing our understanding of fundamental physics and helping us better comprehend phenomena throughout the cosmos. As you stand there watching the aurora dance across the sky, you're witnessing the end result of a chain of events that began on the Sun and traveled through 93 million miles of space to reach Earth. The light you see is the final act in a drama that involves nuclear fusion in the Sun's core, magnetic field dynamics throughout the solar system, and the complex interactions between charged particles and atmospheric gases. The aurora above you is also a reminder of the delicate balance that makes life on Earth possible. Our planet's magnetic field, which creates these beautiful displays, also protects us from the constant bombardment of high-energy particles from space. Without this protection, our atmosphere would gradually be stripped away by the solar wind, leaving Earth as barren as Mars. Recent research has shown that the strength of Earth's magnetic field has varied throughout our planet's history, and there have been periods when the field was much weaker or even reversed completely. During these times, auroras would have appeared at very different latitudes, and the amount of cosmic radiation reaching Earth's surface would have been much higher. Some scientists speculate that these periods of magnetic weakness may have influenced the evolution of life on our planet. The aurora you're observing is also connected to phenomena much closer to home. The same magnetic field that creates auroras also influences weather patterns, animal migration, and even human behavior. Many animals use Earth's magnetic field for navigation, and some research suggests that changes in magnetic activity may affect everything from bird migration patterns to the timing of biological processes in various organisms. As the aurora continues its dance above you, the colors shifting and pulsing in response to the invisible forces at work in the magnetosphere, you're witnessing one of nature's most perfect examples of the interconnectedness of all things. The light in the sky connects you to the sun, to the cosmos, and to the fundamental forces that govern the universe itself. The aurora is also a bridge between the ancient and the modern, between the mythological and the scientific. For thousands of years, humans have looked up at these lights with wonder and created stories to explain them. The Inuit spoke of the spirits of the dead playing in the sky, while Norse mythology described the aurora as the reflection of light from the shields of the Valkyries. Today, while we understand the scientific mechanisms behind these displays, they remain no less wondrous or inspiring. Standing there in the Arctic night, watching the aurora dance across the star-filled sky, you're part of a tradition that stretches back to the earliest humans who looked up at these lights with awe and curiosity. The aurora connects us to our ancestors and to future generations who will continue to marvel at these celestial displays long after we're gone. As the night progresses and the aurora continues its eternal dance, you become aware that you're witnessing something that speaks to the very heart of what it means to be human. Our capacity for wonder, our desire to understand the world around us, and our ability to find beauty and meaning in the vast cosmos of which we are a part. The dance of charged particles through our atmosphere creates one of nature's most captivating spectacles. Yet behind these shimmering curtains of light lies a story of cosmic forces that connects us to the very heart of our solar system. Tonight, we delve into the mysteries of the aurora, those ethereal lights that have whispered to humanity across millennia, painting the polar skies with colors that seem almost too beautiful to be real. The aurora represents far more than a simple light show in the heavens. It is a visible manifestation of the invisible forces that surround and protect our planet, a delicate dance between Earth's magnetic field and the relentless stream of particles flowing from our sun. When these cosmic dancers meet in the thin atmosphere above our heads, they create a symphony of light that has inspired countless myths, legends, and scientific discoveries throughout human history. To understand how these celestial lights come to be, we must first journey to the source of their power, 93 million miles away, where our sun burns with nuclear fire. Deep within the solar core, temperatures reach 15 million degrees Celsius, hot enough to fuse hydrogen atoms into helium and release tremendous amounts of energy. This energy takes thousands of years to work its way from the core to the sun's surface. But once it reaches the solar corona, the sun's outermost atmosphere, it drives a phenomenon that affects every planet in our solar system. The solar wind, a continuous stream of charged particles, flows outward from the sun at speeds exceeding 1 million miles per hour. These particles, primarily protons and electrons, carry with them the sun's magnetic field, stretching it into vast spirals that reach far beyond the orbit of Pluto. This solar wind is not uniform or constant. It varies with the sun's 11-year cycle of activity, sometimes gentle as a cosmic breeze, other times violent as a stellar hurricane. When solar flares erupt from the sun's surface, they can accelerate particles to incredible speeds, creating coronal mass ejections that race through space like cosmic tsunamis. These events can launch billions of tons of solar material into space, and when they're directed toward Earth, they create the conditions for some of the most spectacular aurora displays ever witnessed. The particles from these solar storms can reach Earth in as little as 18 hours, though the journey typically takes 2 to 3 days. As these solar particles approach Earth, they encounter our planet's first line of defense against the harsh environment of space, the magnetosphere. This invisible shield, generated by the churning of molten iron in Earth's core, extends far into space, creating a protective bubble around our planet. The magnetosphere is not a perfect sphere, but rather a teardrop-shaped region that extends about 10 Earth radii toward the sun and stretches into a long tail on the night side of our planet. The interaction between the solar wind and Earth's magnetosphere is a complex dance of electromagnetic forces. Most of the time, the magnetosphere successfully deflects the solar wind, causing it to flow around Earth like water around a stone in a stream. However, when the solar wind carries a magnetic field that points southward, opposite to Earth's magnetic field, something remarkable happens. The two magnetic fields can reconnect, creating gaps in our magnetic shield that allow solar particles to penetrate deep into the magnetosphere. This process, known as magnetic reconnection, is the key that unlocks the door to the aurora. When the solar and terrestrial magnetic fields reconnect, they create pathways along which charged particles can flow toward Earth's poles. These particles follow the magnetic field lines like runners on a track, spiraling down toward the polar regions where the magnetic field lines converge and dive into the atmosphere. The aurora itself occurs when these energetic particles collide with atoms and molecules in Earth's upper atmosphere, primarily between 60 and 400 kilometers above the surface. At these altitudes, the atmosphere is incredibly thin, with densities millions of times lower than at sea level, yet it contains enough gas molecules to create the spectacular light displays we observe. The colors of the aurora depend on which atmospheric gases are struck by the solar particles, and at what altitude these collisions occur. The most common aurora color is green, produced when charged particles collide with oxygen atoms at altitudes between 100 and 300 kilometers. This distinctive green glow comes from a forbidden transition in the oxygen atom, a quantum mechanical process that takes nearly a second to complete, an eternity in atomic terms. Higher in the atmosphere, typically above 300 kilometers, collisions with oxygen produce red light. These red auroras are less common because the atmosphere is extremely thin at these altitudes. But when they do occur, they can create some of the most breathtaking displays, with crimson curtains stretching across the entire sky. The red emissions can extend to altitudes of over 600 kilometers, making them visible from vast distances. Blue and purple hues in the aurora come from nitrogen molecules, which become excited at lower altitudes, typically below 100 kilometers. These colors often appear at the bottom edges of aurora displays, creating a beautiful contrast with the green and red emissions above. The blue light comes from nitrogen molecules that have been ionized by the incoming particles, while the purple comes from a combination of blue nitrogen emissions and red oxygen emissions. The shapes and movements of aurora displays are as varied as they are beautiful. The classic aurora appears as a green arc stretching across the sky, often with vertical rays extending upward like the pipes of a cosmic organ. These rays align with Earth's magnetic field lines, creating the characteristic curtain-like appearance that gives the aurora its ethereal quality. During periods of high solar activity, the aurora can take on more dynamic forms. Corona displays occur when the observer is directly beneath the point where magnetic field lines converge, creating the appearance of rays radiating outward from a central point overhead. Pulsating auroras flicker like cosmic heartbeats, their brightness varying in regular cycles that can last for hours. The aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere are mirror images of each other, occurring simultaneously as particles stream down both sides of Earth's magnetic field. This conjugate behavior means that when observers in Alaska witness a spectacular display, observers in Antarctica at the conjugate point would see a nearly identical show, assuming the skies are clear and dark enough to observe. The intensity and geographic extent of aurora displays vary dramatically with solar activity. During solar minimum, when the sun is relatively quiet, auroras are typically confined to high latitudes, visible primarily in places like northern Canada, Alaska, northern Scandinavia, and Antarctica. But during periods of intense solar activity, particularly during major geomagnetic storms, the aurora can expand to much lower latitudes, occasionally becoming visible as far south as the northern United States or even southern Europe. These geomagnetic storms represent some of the most powerful space weather events in our solar system. When a particularly strong coronal mass ejection strikes Earth's magnetosphere, it can compress the magnetic field and inject enormous amounts of energy into the magnetosphere. This energy eventually finds its way into the atmosphere, creating aurora displays of exceptional brightness and extent. The Great Geomagnetic Storm of 1859, known as the Carrington Event, produced auroras visible as far south as the Caribbean and Hawaii. Telegraph systems failed across North America and Europe, with some operators receiving electric shocks from their equipment. The aurora was so bright that people could read newspapers by its light, and some observers reported that the aurora was initially mistaken for the glow of distant fires. Modern technology has given us unprecedented insight into the aurora phenomenon. Satellites positioned throughout Earth's magnetosphere continuously monitor the solar wind and the behavior of charged particles in space. Ground-based instruments, including all-sky cameras and magnetometers, track aurora activity around the clock. These observations have revealed that the aurora is not just a beautiful light show, but a visible manifestation of fundamental plasma physics processes that occur throughout the universe. The aurora also serves as a natural laboratory for studying plasma physics, the behavior of charged particles in magnetic fields. The same processes that create the aurora also occur in the magnetospheres of other planets, in the atmospheres of stars, and in the vast spaces between galaxies. By studying the aurora, scientists gain insights into phenomena that occur on scales from planetary to cosmic. Recent discoveries have revealed new types of aurora phenomena that challenge our understanding of magnetospheric physics. STEVE, an acronym for Strong Thermal Emission Velocity Enhancement, appears as a narrow purple ribbon stretching across the sky, often accompanied by green picket fence structures. Unlike traditional auroras, STEVE appears to be caused by hot plasma flowing at tremendous speeds through the magnetosphere. The aurora continues to inspire and mystify us, serving as a bridge between the scientific and the sublime. Indigenous peoples of the Arctic have developed rich mythologies around the aurora, seeing in its movements the spirits of ancestors, the breath of whales, or the pathway souls take to the afterlife. These cultural interpretations remind us that the aurora is not just a subject for scientific study, but a phenomenon that touches something deep in the human experience. For those fortunate enough to witness the aurora firsthand, the experience is often described as life-changing. The silence of the polar night, broken only by the subtle crackling sounds that some observers report hearing during intense displays, creates an atmosphere of profound connection with the cosmos. Standing beneath the dancing lights, one cannot help but feel part of something much larger than oneself, a participant in the cosmic dance that connects our small planet to the vast universe beyond. The aurora reminds us that Earth is not an isolated world, but an active participant in the solar system's dynamic environment. The same magnetic field that protects us from harmful solar radiation also channels solar particles into our atmosphere, creating these magnificent displays. In this way, the aurora represents both our planet's vulnerability to space weather and its remarkable ability to transform potentially destructive forces into breathtaking beauty. As we continue to explore space and develop new technologies, our understanding of the aurora will undoubtedly deepen. Future missions to other planets will reveal how aurora phenomena manifest in different atmospheric and magnetic environments. The aurora of Jupiter, powered by the giant planet's rapid rotation and strong magnetic field, creates displays thousands of times more powerful than Earth's aurora. Saturn's aurora, influenced by its complex ring system and numerous moons, exhibits behaviors unlike anything seen on Earth. The aurora stands as a testament to the interconnectedness of our solar system and the elegance of the physical laws that govern cosmic phenomena. In its dancing lights, we see the marriage of solar energy and terrestrial magnetism, the collision of particles and atoms, the emission of photons that have traveled millions of miles to paint our sky with colors that exist nowhere else in our earthly experience. Tonight, as you rest beneath the same magnetic field that guides the aurora's dance, remember that you are part of this cosmic story. The elements in your body were forged in stellar cores. Your planet's magnetic field extends far into space, and the very air you breathe participates in the delicate atmospheric chemistry that creates the aurora's glow. Tonight, we journey into the realm where Earth meets the heavens, where charged particles from our sun dance with our planet's magnetic embrace to create one of nature's most ethereal displays. We have explored the cosmic architecture of dark matter, witnessed the birth of stellar nurseries, and marveled at gravity's patient choreography across the universe. Now we turn our attention to a phenomenon that brings the cosmos directly to our doorstep, painting the polar skies with whispers of light that have captivated humanity since we first looked up in wonder. The aurora represents something profound about our place in the universe. Here is a celestial light show that occurs not in the distant depths of space, but right here in our own atmosphere, a direct manifestation of the invisible forces that connect our small world to the vast cosmic web we've been exploring. These dancing lights are messengers from the sun, carrying news of stellar storms and magnetic tempests across 93 million miles of space to paint stories across our polar skies. To truly appreciate the aurora's gentle beauty, we must first understand the stage upon which this cosmic drama unfolds. Our Earth, that pale blue dot suspended in the cosmic dark, is not simply a lonely rock spinning through the void. It is a dynamic, living world wrapped in an invisible shield of magnetism, a protective cocoon that has sheltered life for billions of years. This magnetic field, generated deep within our planet's molten core, extends tens of thousands of miles into space, creating what scientists call the magnetosphere. Picture, if you will, a vast bubble of magnetic influence surrounding our world. This magnetosphere is not a simple sphere, but rather a complex dynamic structure that changes constantly as it interacts with the solar wind, that stream of charged particles that flows continuously from our sun. The solar wind, composed primarily of protons and electrons racing through space at speeds of several hundred kilometers per second, carries with it the magnetic field of our star, creating an invisible highway of energy that connects every world in our solar system. When the solar wind encounters Earth's magnetosphere, something beautiful happens. The interaction is not violent or destructive, but rather like a cosmic dance, a gentle interplay of magnetic forces that has been choreographed over billions of years. The magnetosphere deflects most of the solar wind around our planet, like water flowing around a stone in a stream. But some particles find their way through this magnetic shield, guided along the field lines toward our planet's polar regions. These charged particles, accelerated by the complex magnetic processes occurring in the magnetosphere, stream down through the thin upper atmosphere, where they encounter the gases that surround our world. When these cosmic visitors collide with oxygen and nitrogen atoms in the atmosphere, they transfer their energy, causing the gases to glow with characteristic colors. Oxygen produces the familiar green that dominates most auroral displays, while nitrogen contributes blues and purples to the celestial palette. The aurora is not simply random light scattered across the sky, but rather a carefully orchestrated display that follows the invisible magnetic highways that connect our planet to space. The lights appear in oval-shaped regions around the magnetic poles, creating what scientists call the auroral oval. This oval expands and contracts with the intensity of solar activity, sometimes bringing the aurora to latitudes where it is rarely seen, sometimes confining it to the highest polar regions. What makes the aurora particularly fascinating is its connection to the rhythms of our sun. Our star is not the steady, unchanging beacon it might appear to be from our earthbound perspective. Instead, it is a dynamic, ever-changing ball of plasma driven by magnetic forces that create an 11-year cycle of activity. During periods of high solar activity, the sun erupts with solar flares and coronal mass ejections, sending billions of tons of charged particles racing toward Earth at incredible speeds. When these solar storms encounter our magnetosphere, they can trigger some of the most spectacular auroral displays ever witnessed. The normally gentle auroral oval can expand dramatically, bringing the northern lights to latitudes as far south as the northern United States, or the southern lights to regions where they are typically never seen. These are the moments when the aurora reveals its true power, when the invisible connection between Earth and Sun becomes visible to anyone who simply looks up at the night sky. The colors of the aurora tell a story of atmospheric chemistry and physics that spans from the surface of our planet to the edge of space. The familiar green glow occurs when solar particles collide with oxygen atoms at altitudes of around 100 to 300 kilometers above Earth's surface. At higher altitudes above 300 kilometers, oxygen produces a deeper red glow, while nitrogen creates blue and purple hues at lower altitudes. The exact colors and their intensity depend on the energy of the incoming particles and the density of the atmosphere at different altitudes. But the aurora is more than just a beautiful light show. It represents a direct connection between Earth and the cosmos, a visible manifestation of the invisible forces that shape our solar system. The same magnetic reconnection processes that create the aurora also drive the evolution of planetary magnetospheres throughout the universe. The charged particles that create the dancing lights are part of the same solar wind that has shaped the atmospheres of Mars and Venus and continues to influence the development of planets around other stars. The aurora also serves as a window into the physics of plasma, that fourth state of matter that dominates the universe beyond our small rocky world. In the aurora, we can observe directly the behavior of charged particles as they interact with magnetic fields, providing insights into processes that occur throughout the cosmos, from the surfaces of distant stars to the vast spaces between galaxies. Modern research has revealed that the aurora is part of a complex system of interconnected phenomena that extends throughout the solar system. The same processes that create Earth's aurora also generate similar displays on Jupiter, Saturn, and other planets with strong magnetic fields. The Jovian aurora, powered by the giant planet's incredibly strong magnetic field, and its volcanic moon, Io, can be thousands of times brighter than Earth's aurora, creating a cosmic light show that would be visible from interplanetary space. The study of the aurora has also deepened our understanding of space weather, the way that solar activity affects technological systems throughout the solar system. The same magnetic storms that create beautiful auroral displays can also disrupt satellite communications, interfere with GPS navigation, and even cause power grid failures on Earth. Understanding the aurora helps us predict and prepare for these space weather events, protecting the technology that modern civilization depends upon. As we continue to explore the cosmos and search for life beyond Earth, the aurora takes on even greater significance. The interaction between stellar winds and planetary magnetic fields may be one of the key factors that determines whether a world can maintain the stable atmosphere necessary for life. Planets with strong magnetic fields like Earth can protect their atmospheres from the erosive effects of stellar winds, while planets without such protection, like Mars, may gradually lose their atmospheres to space. The aurora represents something profound about our place in the universe. It reminds us that we are not isolated on our small world, but are intimately connected to the cosmic forces that shape the galaxy. Every auroral display is a message from the sun, a reminder that we live within the extended atmosphere of our star, bathed in its magnetic influence and charged particle flow. Tonight, as you rest under the blanket of Earth's protective magnetosphere, remember that far above the northern and southern polar regions, the aurora may be dancing across the sky, painting stories of cosmic connection in curtains of green and red light. These whispering lights in the polar darkness are messengers from the sun, carrying news of stellar storms and magnetic tempests across the vast emptiness of space to create one of nature's most beautiful displays. The aurora is a bridge between Earth and cosmos, a visible manifestation of the invisible forces that connect our small world to the vast universe beyond. In its gentle glow, we can see the same magnetic processes that shape galaxies, the same charged particle interactions that occur throughout the cosmos, and the same delicate balance between stellar influence and planetary protection that may determine the fate of life throughout the universe. As we drift towards sleep, let us carry with us the image of the aurora dancing across the polar skies, a reminder that we are part of something vast and beautiful, connected to the sun and stars by invisible threads of magnetic force and charged particle flow. In the final chapter of our cosmic journey, we arrive at the grand culmination of auroral understanding, where the whispers of charged particles dancing with Earth's magnetic field reveal the deepest truths about our planet's place in the universe. These luminous displays, those ethereal curtains of green and red and purple light that grace our polar skies, represent far more than mere atmospheric phenomena. They are the visible manifestation of forces that connect us intimately to the very heart of our solar system and beyond. The aurora stands as Earth's most eloquent interpreter of space weather, translating the invisible language of solar wind into poetry written across the darkness. When coronal mass ejections hurtle through interplanetary space at speeds exceeding 1,000,000 miles per hour, carrying with them the magnetic fingerprints of our star's turbulent surface, it is the aurora that announces their arrival. These charged messengers, protons and electrons torn from the sun's outer atmosphere, stream toward Earth in a solar wind that never ceases, carrying energy that could power human civilization for millennia. Yet our planet does not stand defenseless against this cosmic bombardment. The magnetosphere, that invisible shield generated by the churning of molten iron deep within Earth's core, deflects the majority of these particles, creating a protective bubble around our world. This magnetic field, invisible to our eyes but revealed through the aurora's dance, extends far into space, creating a complex three-dimensional structure that scientists are only beginning to fully understand. The field lines that emerge from Earth's magnetic poles stretch tens of thousands of kilometers into space before curving back to complete their circuit, creating highways along which charged particles travel from the outer reaches of the magnetosphere down into our atmosphere. The aurora occurs when these guided particles, accelerated to tremendous speeds by the magnetic field's geometry, collide with atmospheric gases at altitudes between 60 and 400 kilometers above Earth's surface. Oxygen atoms, struck by incoming electrons, emit the characteristic green light that dominates most auroral displays, while nitrogen contributes the blues and purples that add complexity to the spectacle. The precise colors depend on the energy of the incoming particles and the altitude at which collisions occur, creating a palette that ranges from the pale yellow-green of low-energy interactions to the deep red of high-altitude oxygen emissions. But the aurora is more than a simple collision between particles and atmosphere. It is a window into the fundamental physics that governs our universe. The same processes that create auroral displays operate throughout the cosmos, from the magnetospheres of other planets to the accretion disks around black holes. Jupiter's auroras, powered by the planet's rapid rotation and strong magnetic field, dwarf anything seen on Earth, while Saturn's auroras dance to the rhythm of solar wind variations and the gravitational influence of its many moons. These planetary auroras teach us that the processes we observe in our own sky are universal, operating wherever magnetic fields and charged particles interact. The study of auroras has revealed the intricate connection between solar activity and terrestrial phenomena. The 11-year solar cycle, driven by the complex dynamics of the sun's magnetic field, directly influences the frequency and intensity of auroral displays. During solar maximum, when the sun's magnetic field is most tangled and unstable, coronal mass ejections become more frequent and powerful, expanding the auroral oval and bringing the northern and southern lights to latitudes where they are rarely seen. These geomagnetic storms can disrupt satellite communications, interfere with GPS navigation, and even cause power grid failures, demonstrating that the aurora is not merely a beautiful light show, but a visible indicator of space weather that affects our technological civilization. The aurora also serves as a natural laboratory for studying plasma physics, the science of ionized gases that make up 99% of the visible universe. The same electromagnetic processes that accelerate particles in Earth's magnetosphere operate in stellar atmospheres, planetary magnetospheres, and the vast spaces between galaxies. By studying auroral phenomena, scientists gain insights into how magnetic fields store and release energy, how charged particles are accelerated to high speeds, and how electromagnetic waves propagate through space. These discoveries have applications ranging from controlled nuclear fusion to understanding the behavior of distant quasars and gamma-ray bursts. The cultural significance of auroras extends far beyond their scientific importance. For indigenous peoples of the Arctic, The Northern Lights have been woven into spiritual beliefs and traditional knowledge for thousands of years. The Inuits speak of the aurora as the spirits of the departed playing ball with a walrus skull, while Scandinavian folklore describes the lights as reflections from the shields of the Valkyries. These cultural interpretations remind us that the aurora has been inspiring human imagination and wonder since our species first looked up at the night sky, long before we understood the electromagnetic processes that create these displays. In our modern era, the aurora continues to inspire artists, photographers, and travelers who journey to the polar regions in search of the perfect auroral display. The rise of aurora tourism has brought economic benefits to communities in Alaska, northern Canada, Scandinavia, and other high-latitude regions, while also raising awareness of the fragility of the environments where auroras are best observed. Climate change threatens to alter the atmospheric conditions that affect auroral visibility, while light pollution from expanding cities diminishes the contrast needed to observe fainter auroral forms. The aurora also represents a bridge between Earth and space, a visible reminder that our planet exists within a dynamic solar system where conditions are constantly changing. The charged particles that create auroral displays have traveled millions of kilometers from the Sun, carrying with them information about solar magnetic fields, coronal temperatures, and the structure of the solar wind. In this sense, every aurora is a message from our star, encoded in the language of electromagnetic phenomena and decoded by the interaction between solar particles and Earth's magnetic field. As we continue to explore the solar system and search for life beyond Earth, the aurora takes on new significance as a potential indicator of habitability. Planets with strong magnetic fields and substantial atmospheres may host their own auroral displays, suggesting the presence of conditions that could support life. The detection of auroral radio emissions from exoplanets may eventually provide us with a new tool for studying distant worlds and assessing their potential for harboring life. The aurora reminds us that Earth is not an isolated world, but an integral part of a vast cosmic ecosystem where energy and matter flow constantly between the Sun, the planets, and the space that surrounds them. The magnetic field that protects us from harmful solar radiation and creates the conditions for auroral displays is itself generated by the same geological processes that have shaped our planet's surface and made it habitable for life. In this sense, the aurora represents the visible manifestation of the deep connection between Earth's interior, its atmosphere, and its place in the solar system. In the farthest reaches of the northern and southern skies, a silent ballet of light unfolds, delicate, dancing, and older than memory. These shimmering veils of green, pink, violet, and crimson are known as auroras. On Earth, we call them the aurora borealis in the north and the aurora australis in the south. But beyond the poetry and beauty lies a story of magnetic fields, solar winds, and a cosmic connection between our sun and planet. It's a mystery written in light, one that stretches across space, guided by invisible forces that shape more than we see. Long before scientists explained their cause, humans gazed upward and assigned auroras divine meaning. In Norse mythology, they were the reflections of Valkyrie armor. In Inuit traditions, the lights were spirits playing ball in the sky. In ancient China, they were celestial battles between dragons. These stories echo the awe we still feel today, because even with science, the mystery of the aurora remains something felt more than understood. The real story begins not on Earth, but with the Sun. Our star is far from calm. It constantly emits a stream of charged particles, known as the solar wind. This wind is made of electrons and protons, traveling at over 1 million miles per hour. It flows outward, through the solar system, touching every planet it encounters. But Earth has a shield, a magnetic bubble called the magnetosphere, and it's this shield that gives rise to the aurora. When solar particles approach Earth, most are deflected by the magnetosphere, but near the magnetic poles, the field lines curve downward, funneling particles into the upper atmosphere. There, roughly 60 to 300 miles above the surface, those particles collide with gases, mostly oxygen and nitrogen. The energy from the collisions excites the gas atoms, and as they return to their normal state, they release photons, tiny packets of light. The result is an aurora. The colors of an aurora depend on altitude and the type of gas involved. Green, the most common color, is produced by oxygen around 100 kilometers up. Red occurs at higher altitudes, also due to oxygen, but under different conditions. Blue and purple hues come from nitrogen. The particular mix of light forms the signature curtain-like patterns that seem to ripple and move as if alive. But auroras are not constant. They ebb and flow, influenced by solar activity. During periods of heightened solar output, known as solar storms or coronal mass ejections, Earth's skies can be filled with dazzling displays that reach far beyond the usual polar regions. In 1859, a massive solar storm, known as the Carrington event, caused auroras visible as far south as Cuba and Hawaii. Telegraph systems sparked and failed. If a similar storm struck today, satellites, power grids, and communication networks could all be at risk. Modern science uses satellites like NASA's Themis and ESA's Cluster mission to monitor auroral activity from above. These instruments have revealed that auroras are even more dynamic than they appear from the ground. Explosive magnetic events in space, known as substorms, cause sudden brightening and movement in the aurora. These substorms are triggered when the solar wind stretches Earth's magnetic field until it snaps back, like a rubber band, flinging particles toward the poles. Auroras aren't unique to Earth. They've been spotted on Jupiter, Saturn, Uranus, and Neptune, giant planets with strong magnetic fields. Even Mars, which has only remnant magnetism, displays faint auroral activity. But Earth's auroras remain the most vivid and accessible, dancing in the night sky above Alaska, Canada, Scandinavia, and Antarctica. Some researchers study auroras not just for their beauty, but for what they reveal about the invisible space weather surrounding Earth. As technology grows more dependent on satellites and wireless systems, understanding and forecasting these interactions becomes increasingly critical. A large enough geomagnetic storm could disrupt navigation systems, aviation routes, and even power plants. Yet despite their importance, auroras retain their magic. Time-lapse footage often fails to capture the subtlety of motion visible to the naked eye. The lights seem to respond to thought, pulsing, whispering, even shifting shape as if reacting to your gaze. In truth, they follow the contours of Earth's magnetic field, which itself is in constant motion, always reshaped by the forces of the sun. There's also the sound. While auroras are mostly silent, some observers report faint crackling noises, like static or whispering. Scientists have only recently begun to study this phenomenon. The sounds may come from low-frequency electromagnetic waves interacting with the atmosphere, or even directly with the human auditory system. It's a reminder that even in the silence of night, the sky has more to say. The best place to view auroras is under dark, clear skies far from city lights. Winter months offer the longest nights, especially in the polar regions, but the aurora follows its own rhythm, tied more closely to the sun than to human clocks. Solar cycles, periods lasting roughly 11 years, control the intensity and frequency of auroral displays. As of now, we are entering a period of increased solar activity, promising more vivid skies ahead. Auroras are also a symbol of unity, a shared spectacle that connects people across time and culture. Pilots, scientists, explorers, and dreamers have all watched them, often from opposite ends of the globe, under identical skies. No two auroras are the same, and yet they all echo the same cosmic song, one of energy, motion, and transformation. In an age of artificial light, there's something ancient about standing beneath the aurora. It pulls us back to a time when the stars were not just scenery, but stories. It reminds us that we are part of a greater system, one that hums with electricity and dances with light, one that links the molten heart of the sun with the frozen poles of Earth in a grand, silent conversation. Perhaps that's the most profound truth about auroras. They are not just atmospheric phenomena. They are messages, reminders that our world is alive, reactive, and deeply connected to the universe around it. When the sky lights up, it's not just a display, it's an echo from the stars, touching Earth with a gentle finger of fire. So the next time the sky pulses green or red, don't just look up. Feel it. Know that you're witnessing one of nature's rarest miracles, a moment when light, space, and Earth become one. In the stillness of night, the aurora tells a story older than language. And for those who listen, it never truly ends. As we stand beneath the dancing lights of the aurora, we are witnessing the intersection of solar physics, planetary science, atmospheric chemistry, and electromagnetic theory. We are seeing the sun's influence made visible, Earth's magnetic protection demonstrated, and the fundamental forces of nature transformed into beauty. The aurora whispers to us of the cosmic forces that have shaped our world and continue to influence our planet's evolution, reminding us that we are part of a universe where everything is connected, where the behavior of distant stars affects conditions on Earth, and where the dance of charged particles in space creates some of the most beautiful phenomena our world has to offer. In the end, the aurora stands as Earth's luminous signature in the cosmos, a unique expression of our planet's magnetic personality and its relationship with the sun. These whispering lights in the sky tell the story of our world's place in the universe, of the invisible forces that protect and sustain life, and of the beauty that emerges when the cosmos and our planet dance together in the eternal choreography of space and time. The aurora is both a scientific phenomenon and a work of art, both a window into fundamental physics and a source of wonder that connects us to the grander scales of the universe, reminding us that we live on a magnetic planet in a dynamic solar system within a cosmos filled with light and energy and beauty beyond our wildest imagination. So now, as your thoughts drift like solar winds across a sleeping Earth, let the last traces of the aurora linger in your mind. These glowing rivers of light, born from the stars and shaped by our planet's invisible shield, remind us how even in darkness, nature finds a way to dance. Close your eyes, rest easy, and remember, the universe is always speaking. Sometimes in silence, and sometimes in shimmering waves of light above the poles. Good night, and thank you for watching Boring Science and Cheers.